The objectives of this chapter first is to understand the basic objective and the scope of the computer graphics, to identify computer graphics application, to understand the basic structure of 2D and 3D graphic system, to understand the evolution of graphic programming environments, to identify common graphics APIs, to understand the roles of Java language, Java 2D and Java 3D packages, and at last to identify computer graphic related fields. Computer graphics studies the theory and techniques of modeling, processing, and rendering of graphical objects in computers. The basic objective of computer graphics is to build a virtual world of graphics objects and to render a scene of the virtual model from a specific view on a graphic device. As you can see in this figure, a graphic system consists of two major components, a modeler and a renderer. The modeler is responsible for the construction of virtual model, and the renderer performs the rendering of the scene. The basic components and functions of the graphical system is the modeler, the renderer, the hardware devices, the virtual world, the view, the geometry, transformation, illumination, interaction, and animation. Graphic objects to be modeled are in either a 2D or a 3D space. This common space to host all the graphic objects is often called the world space. The graphics objects to be modeled in a world space are usually geometric entities like lines and surfaces, but they also can include a special objects like light, text, and images. The graphics object may process many characteristics and properties such as color, transparency, and texture. Also, we can use various mathematical representations that use to model a geometric object. We can use a spline curve and surfaces that require only the storage of a relatively few control points. The components of graphic systems are the modeler that is responsible for the construction of virtual world model. Modeling, which means the process of constructing a graphics model. The renderer, that is perform the rendering of the scene. The rendering, which means the process of constructing an image of a scene from a graphics model. The object transformation are geometric transformation applied to an object to achieve proper displacement of the object in a virtual space, such as rotation, translation, shearing, etc. All these transformations will be seen in the next chapter. GUI, which is the graphical user interface, is based on the user interaction with the graphic system. Geometric transformations are applied to the object to achieve a specific displacement in the virtual model. Transformation of this type are called object transformation. Then, object transformation is the mapping of the object spaces into world space, that is the common coordinate system for all objects. Transformations are also used for the viewing. This is known as viewing transformation. Viewing transformation then is the transformation from the world space to the device space. A useful family of the geometric transformation is the affine transformation, which include the most common type as translation, rotation, scaling, and reflection. A more general set of transformation, the projective transformation, which is useful in 3D viewing, which is not in our scope of course. A view is used to see the model in the virtual world from a specific perspective. we have the 2D view and the 3D view. The 2D view is relatively simple. Viewing transformation is indistinguishable from the object transformation. Rendering features such as composition rules and clipping paths may be applied to 2D view. However, the 3D view is more complicated. It looks like eyes or cameras. It involves a projection process that maps 3D object to a 2D plane. Projection, view position, orientation, and field of view could affect the 3D rendering. The capabilities and characteristics of hardware devices have a great impact on graphic systems. The most common output devices for displaying the result of graphics rendering are video monitors, printers, and plotters. Other output devices include holographic projectors also. For input devices, we have the mice, joysticks, and tablets with pen are widely available. There are also more sophisticated input devices and sensors such as the 6 degree of freedom trackers, which are the 6 coordinates of an object to specify the position of an object. Animation is also an important part of computer graphics. Instead of still images, animation produces dynamic graphic contents and rendering. In applications such as movie screen rendering and gaming animation plays an important role. Another dynamic aspect of computer graphics is interaction. In response to user input, the graphics model may change accordingly. The fundamental principle of graphical user interface is based on the user interaction with graphics system. Another example of extensive application of interaction is the video game. Computer graphics has a wide range of applications. The popularity of graphical user interface environment has made graphics an integral part of ordinary user programs. In addition to CAD, which is a computer-aided design, and other engineering applications depends on graphics systems. Also, we have some medical systems like the CT and PET and MRI are medical systems that has increasingly employed computer graphics technologies. In addition, the computer graphics is also used in video games and other entertainment applications. Graphics programming has appeared in almost every level of computer architecture. Generally, it is moving from low-level platform-dependent methods toward abstract, high-level, and portable environments. As we can see, we will see different graphics programming environments at various levels of computer architecture, and each one of these environments will be described in the following slide. We will see the hardware, level, the operating system level, the graphics standard level, and the platform independent level. We will begin discussing the hardware level. Computer graphics programs depend on output devices with graphical capabilities. We can use the most display devices, which are the CRT, which are cathode ray tube monitors, and the LCD liquid crystal display panels. Low-level graphics applications often program the graphic hardware directly. In the popular environment of personal computing running MS-DOS, most graphic applications directly access the display memory. Such programs are typically written in assembly language and manipulate the hardware registers and video buffer in a highly machine-dependent way. If, for example, we want to draw a circle using MS-DOS graphics program, we can determine the pixels of the circles. From a current pixel, we can determine the next pixel, which can be either east or southeast. Between the two pixels, the one closer to the curve is selected. Now we will talk about the second level, which is the operating system level support. The low-level graphic infrastructure seen before provides basic facilities for programming the display. However, directly programming video buffers and hardware register is not an effective approach for graphic applications. So programming at the hardware level require a knowledge of the device. Programs written at these levels are not portable even for different devices in the same platform. So we can say that we can use a high-level language interface for graphic programming applications. With the development and widespread of applications of graphical user interface applications, in modern computers, graphics support in operating system has become common and extensive. So, graphics APIs provided at the operating system level offer a uniform interface for graphic programming within the same platform. So, as we can see in the example, Win32 is the API for 32-bit Windows operating system. This example is a simple window program written in the C language. The program creates a standard window and calls Win32 API directly to draw a circle in the client area of the main window program. The circle is centered in the window and the size is adjusted automatically if the window is resized. The problem with the operating system level is that the graphics program that relies on the operating system are not portable across the platform. For example, in Windows and Mac's operating system, APIs are different. Now we will talk about OpenGL level. OpenGL is a popular 2D 3D graphics API derived from GL, which is the graphic library of Silicon Graphics. GL is the graphics programming interface used on successful graphics workstations. OpenGL is designed to be an open standard. It is available virtually on all computer platforms. Many hardwares offer OpenGL interface for their graphics cards and devices. With OpenGL, we have over 200 functions. OpenGL provides a much more powerful graphic API than the GKS. OpenGL is a relatively low-level API. Different languages are used in OpenGL. The official language is Fortran, and now under the development of Java binding. However, the deep root of OpenGL is the C language. OpenGL consists of two libraries, GL and GLU. The GL library contains the core functions for the basic graphic features, and the GLU contains the higher level utility functions. OpenGL itself does not have functions for constructing a user interface, so a simple portable package called GLUT can be used with OpenGL to construct a complete graphic program. OpenGL provides a standard and efficient rendering interface to graphics hardware. However, with the rapid development of computer hardware and software technologies, high-level abstraction of graphics programming is now feasible. So, a high-level object-oriented programming based graphic API may offer great benefit to application programmers. Java 2D and Java 3D are newer graphics APIs associated with the Java programming language. They are high-level object-oriented with high portability. So, Java 3D based graphic system implemented on the top of API such that OpenGL. Java 2D and Java 3D will be API that will be used in this course. The following table shows a typical graphic system layout. As we can see, here we have the hardware level. Okay, then the operating system level, where OpenGL and Java the Java are built on. To have at last at the topic, which is Java 3D and Java API. In recent years, Java has gained enormous popularity and has quickly become the programming language of choice for a wide range of applications. A Java program is compiled to a standard platform-independent format called bytecode. The compiled bytecode can be executed without any change on any machine with a Java virtual machine, which is the JVM. This platform independent makes Java the ideal language for applications over the internet. Also, Java is designed from the ground up to support object-oriented programming. So Java is a program consists of classes definitions. Java also maintains the simplicity, elegance, and efficiency of its precedent languages like C or C++. So Java is a very simple language. The Java platform offers a comprehensive set of APIs. The Java APIs covered a wide range of tasks and applications like file input, output, graphics, multimedia, database, networking, and security. Java contains two nearly parallel sets of facilities, which are the AWT and the Swing. AWT, which is an early version of Java, it offers a limited graphics support, offer capabilities to control certain rendering attributes such as drawing colors and to draw some graphics primitives such as line, rectangles, and ovals. However, the features are limited. For example, there is no way to control the width of drawing lines because of the limitation of this version. We have also the Swing package, which is a completely redesigned graphical user interface programming. It includes included in the Java 2D platform. The graphics support in Java 2D is also enhanced. The Java 2D packages provide comprehensive 2D graphic features. So Swing is a completely redesigned graphical user interface programming API included in the Java 2D platform. Okay, one graphic programming option for Java is OpenGL. There are several projects to develop Java language binding for OpenGL. So GOGL, which is Joggle, which is Java OpenGL based on Java. Joggle provides the classes GL and GLU to encapsulate the functions in GL and GLU. The two components, GL Canvas and GLJ panel, provide the drawing surfaces for the OpenGL code. First, the GL Canvas is a heavy component that will use the hardware acceleration. However, the GLJ panel is a lightweight component implemented in memory. No hardware acceleration is available to GLJ panel. A typical procedure for programming Joggle is outlined below. First, we create a GL Canvas or GLJ panel object through the GL Drawable Factory class. Then we add a GL event listener to the Canvas object. And at last, we implement the listener by implementing the four methods in its display, reshape, and display change. The Java 2 platform brings significant improvement in graphics capabilities with the introduction of Swing and Java 2D and 3D APIs. The well-designed APIs offer comprehensive support for many tasks of computer graphics. Together with the unique advantage of the Java programming language, they have made the combination of Java with Java 2D and Java 3D a very attractive option for graphic programming and learning computer graphics. So the graphic support in earlier versions of Java is very primitive and limited. However, Java 2D provides a complete set of functionalities to manipulate and render 2D graphics. The enhancements include a separate class for geometric objects is defined in Java 2D. The rendering process is much more refined. Complete new image processing features are introduced. Also, a color model, font, printing, and other graphics related support are also greatly improved. The Java 2D class, which is a subclass of the graphics class, is the rendering engine for Java 2D. It provides methods to render geometric shapes, image, and text. The rendering process can be controlled by selecting transformations, paint, line properties, composition, flipping, path, and other properties that will be seen during this course. The Swing component and Java 2D included in the Java 2 platform are more advanced than the graphics facilities in earlier Java versions. The Java 2D examples in this course will use the Swing and avoid the use of old AWT components. Java 3D is an optional package of the Java platform. Java 3D provides comprehensive framework for 3D graphics, including animations, 3D interactions, and sophisticated viewing. An abstract model known as the skin graph is used to organize and retain the visual objects and behaviors in the visual scene. The scene graph contains the complete information of the virtual graphics world. The Java 3D rendering engine renders the skin graph automatically. So the visual effects of the program are achieved by creating a scene graph and placing the appropriate graphics elements into it. The skin graph for the program is a tree-like structure containing objects such as the sphere, the 3D text, appearance, transformation, backgrounds, and light. The rendering of the scene is done automatically by the Java 3D engine. So the concept and technique of programming Java 3D with scene graph will be introduced in the later chapters. We will see the modular renderer and how we can integrate Java in graphics. Other fields related to graphics, computer graphics, image processing, and computer vision are all computer-related fields that deals with graphical objects. They are different in their objectives and techniques. However, close relationships exist among them, and the line between them has been increasingly blurred. Image processing is concerned with techniques of processing digital images. It typically deals with problems such as image enhancement, noise reduction, edge detection, and image compression. Image processing takes an existing image as input and perform appropriate action. So the computer graphics, on the other hand, generate a new image from the virtual world. Computer vision attempts to derive an understanding from image of the real world. In a way, a computer vision system is the inverse of a computer graphic system. Its main goal is to reconstruct a virtual world from real-world images. So, computer vision and computer graphics are complementary to each other. They provide different perspectives to a common system. The theory and the practice of computer graphics depend on certain important mathematical concepts, which are the analytic geometry and linear algebra. Analytic geometry provides a numerical representation of graphical objects, and linear algebra studies the operation and transformations of vector space, which are important in many fundamental problems of computer graphics.